Lesson: Model compression and efficiency techniques. Model compression and efficiency techniques are critical in AI performance optimization, especially as the demand for deploying machine learning models on resource-constrained devices increases. These techniques aim to reduce the computational and storage requirements of machine learning models while preserving their accuracy. The importance of these techniques is underscored by the growing trend towards edge computing, where models must operate efficiently on devices with limited processing power and memory. Practical tools and frameworks have been developed to facilitate model compression, each with unique advantages and applications. One of the primary techniques used in model compression is pruning. Pruning involves removing unnecessary weights or neurons from a neural network. This technique can significantly reduce the model's size and improve inference speed without substantially degrading performance. For instance, Han et al. Demonstrated that pruning could reduce the number of parameters in AlexNet by 9x and VGG16 by 13x, with minimal loss in accuracy. The practical application of pruning can be achieved using frameworks such as TensorFlow, Model Optimization Toolkit, and PyTorch's torch.nn.utils.prune. These tools provide interfaces for implementing various pruning strategies, such as weight pruning and structured pruning, enabling practitioners to tailor the compression process to their specific requirements. Quantization is another powerful technique for model compression. It involves reducing the precision of the numbers used to represent the model's parameters. For example, converting 32-bit floating-point numbers to 8-bit integers can drastically reduce the model size and increase computational efficiency, especially on hardware that supports integer arithmetic. The TensorFlow Lite framework offers post-training quantization and quantization-aware training, which can effectively reduce the model size and improve latency on mobile devices. Jacob et al. Reported that quantization could reduce the size of a neural network by up to 4x with negligible impact on accuracy. Knowledge distillation is a technique that involves training a smaller model, referred to as the student model, to mimic a larger, more complex model, known as the teacher model. The student model learns to reproduce the teacher model's outputs, which allows it to achieve comparable performance with significantly fewer parameters. This approach is particularly useful in scenarios where deploying large models is impractical due to resource constraints. Hinton et al. Demonstrated that knowledge distillation could effectively compress large models while maintaining accuracy. Frameworks such as the Hugging Face Transformers library provide tools for implementing knowledge distillation, allowing practitioners to leverage pre-trained models and fine-tune them for specific tasks on smaller architectures. Low-rank factorization is another technique used in model compression. It approximates a weight matrix with a product of two smaller matrices, thus reducing the number of parameters and computational complexity. This technique is particularly useful for compressing large, fully connected, and convolutional layers. Frameworks such as TensorLi provide tools for tensor decomposition, which can be used to implement low-rank factorization in practice. Jaderberg et al. Applied low-rank factorization to convolutional layers and achieved a speedup of 4.5x on CPU with a minimal reduction in accuracy. In addition to these techniques, neural architecture search can be employed to automatically design efficient models tailored to specific hardware constraints. NAS uses reinforcement learning or evolutionary algorithms to explore a vast space of network architectures, identifying those that offer the best trade-offs between performance and efficiency. The AutoML framework by Google provides tools for implementing NAS, enabling practitioners to optimize models for various deployment scenarios. Zoff et al. Illustrated that NAS could create models that outperform manually designed architectures in terms of both accuracy and efficiency. The combination of these model compression techniques can lead to even greater efficiency gains. For example, one might first apply pruning to remove redundant parameters, then quantize the pruned model to reduce precision, and finally use knowledge distillation to transfer the knowledge to a smaller model. This pipeline approach can yield highly efficient models suitable for deployment on edge devices. Real-world applications of model compression and efficiency techniques are diverse. In autonomous vehicles, for instance, models must process sensory data in real time to make driving decisions. Model compression techniques ensure that these models can run on the vehicle's onboard computers without compromising performance. Similarly, in the field of healthcare, deploying AI models on portable medical devices requires efficient models that can operate with limited computational resources. Case studies further illustrate the effectiveness of these techniques. For example, the deployment of AI models in smartphones for applications such as voice recognition and image processing necessitates models that are both compact and fast. By leveraging quantization and pruning, companies like Google and Apple have successfully deployed AI models on their devices, enabling features like real-time language translation and facial recognition without requiring cloud-based processing. Statistics from industry reports highlight the growing adoption of model compression techniques. According to a report by Markets and Markets, the global market for AI and edge computing is projected to grow from $620 million in 2021 to $1.1 billion by 2026, driven by the need for efficient AI models on edge devices. This growth underscores the importance of model compression in meeting the demands of emerging applications. The implementation of model compression techniques requires a strategic approach. Practitioners must consider the specific constraints and requirements of their deployment environment, such as computational power, memory, and latency. By utilizing the appropriate tools and frameworks, they can systematically apply compression techniques to optimize model performance. In conclusion, model compression and efficiency techniques are vital for optimizing AI performance, particularly in resource-constrained environments. Pruning, quantization, knowledge distillation, low-rank factorization, and neural architecture search are among the key techniques that can be employed to achieve this goal. Tools and frameworks such as TensorFlow Model Optimization Toolkit, PyTorch, Hugging Face Transformers, TensorLee, and AutoML provide practical means for implementing these techniques. By understanding and applying these strategies, professionals can enhance their ability to deploy efficient AI models, addressing real-world challenges and advancing their proficiency in AI performance optimization.